So now let's talk about heat engines and the second law of thermodynamics. The second law of thermodynamics can be stated in several ways. The first thing that it's going to say is heat will always flow from hot regions to cold regions spontaneously, without any mechanical work. So we will never see heat flowing from, say, a cold region to a hot region unless you put some work into the system, as we do for refrigerators. The second law of thermodynamics says that must be true. We've never observed that. The other thing the second law of thermodynamics says is that we cannot convert all of the heat that we pull out of a heat engine completely into work. So here we have our hot reservoir, here we have our cold reservoir. It is thermodynamically impossible for all of that heat to be diverted to work. Some of it must go to the cold engine. What that's really saying is we cannot have a 100% efficient engine. This efficiency, that output over input, can never be equal to 1. It always must be less than 1. So the question is how close can we get to a 100% efficiency engine? It turns out that a fellow that was working on steam engines back in about the 1800s or so was interested in designing the perfect engine. So he designed this engine that's going to be called the Carnot engine. It's going to have a Carnot cycle. It's going to have 2 adiabatic segments and 2 isothermal segments. Essentially, what Carnot was doing was he was taking into account that we want to avoid all irreversible processes, so he stuck with adiabatic and isothermal segments only. And on a PV diagram, the Carnot cycle is going to look like this, where we're going to start the gas off right here. It's going to expand isothermally at the temperature of the hot reservoir. It's going to absorb the heat QH right here. Then at point B right here, it's going to start going under, it's going to undergo adiabatic expansion until the temperature drops down here to the cold temperature. Then it's going to be compressed isothermally from C to D, and it's going to reject the heat QC right here, and then it's going to have an adiabatic compression back up to point A. Now, it turns out that the efficiency of the Carnot cycle is related to the temperature of the hot reservoir and the temperature of the cold reservoir with this very important equation right here. The book shows the derivation of that. I'll spare you of that. But you can see how the efficiency is related to the cold divided by the hot. The only way to have a 100% efficient engine is if the temperature of the cold was either absolute 0 or if the temperature of the hot reservoir was infinite, neither of which is physically possible. Taking a look at a Carnot engine that we have over here, we can say, well, suppose I'm interested in figuring out the work that this engine could do. Here I have a hot reservoir and a cold reservoir, so I can very easily calculate what the efficiency of this engine is. It's going to be 1 minus temperature cold over temperature hot, which it gives us these temperatures. Again, must always put these temperatures in Kelvin. So the cold reservoir was at 350 Kelvin, the hot reservoir was at 500. That tells us that the efficiency of our engine is 0.3. Now if I'm interested in how much work I can do, I know that the efficiency is equal to the work divided by QH. I know how much energy it pulls out of the hot reservoir, so the amount of work that is done is simply going to be the efficiency multiplied by QH, or 0.3 multiplied by 2000 joules, and the work that was done is going to then be 600 joules. We can then very easily, using the work in QH, solve for what QC is going to be. So if you take a Carnot engine and you run it in reverse, guess what you have? You have a Carnot refrigerator. And much like the refrigerators we talked about earlier, they're going to have a coefficient of performance. And the coefficient of performance for a Carnot refrigerator is going to be related to the temperatures, temperature cold divided by the difference in the temperatures. More likely than not, I'm going to ask you questions about heat engines over refrigerators simply because I think that they're just more conceptually easier. Okay, the very last topic that we get to talk about is going to be entropy, which is essentially another word for disorder. The only difference between the two is entropy is actually a quantitative measure of how disordered something is. For example, if you had some firecrackers and you light them bad boys off on July 4th, then you can look at the pile of fireworks at the after it's finished exploding and say, yeah, that's pretty disordered. But entropy would actually let us put a number to how much the disorder has changed. So if we talk about reversible processes only for a little bit, then we can say that this entropy, it's actually going to be a change in entropy, that's going to be represented by this delta S. That's how much the entropy has changed in the system. That's going to be equal to the integral of the change in temperature, or change in heat, divided by the temperature. Let's take a look at calculating entropy for melting ice. Let's figure out how much disorder has been introduced by melting ice. Ice starts off in a nice solid ordered crystalline structure. It's going to melt, it's going to lose that crystalline structure, so it's going to become more disordered. You can just kind of see that conceptually thinking about it, but let's put some numbers to it. So the entropy is going to be equal to the integral of the change in heat divided by temperature. Melting ice. Now we know that for ice that the amount of energy that it's going to take is going to be mass of the ice multiplied by the latent heat of fusion for ice. It's actually going to be a constant temperature process. So this integral right here is simply going to become the Q divided by the temperature. Temperature doesn't change when ice is melting. So this simply becomes the mass of the ice multiplied by the latent heat of fusion divided by the temperature of the ice. Have to be careful here, it's not going to be in the Celsius scale, it's going to be in the Kelvin scale, so 273 degrees Kelvin. We're going to say that the mass of the ice is 1 kilogram, and the latent heat of fusion is 3.34 times 10 to the 5th joules, temperatures in kilograms. So at the end of the day, we're going to come up with 1.22 times 10 to the 3rd joules per degree Kelvin. So the change in entropy is going to have a unit of joule per degree Kelvin. For heating water, it's a little bit different. We're going to, heating water is also a reversible process. We're going to say the change in entropy is going to be the integral of dq divided by temperature. Now water is being heated, the temperature is not going to be constant, but we can write how much the energy is going to change. We know that Q is equal to mc delta T, so mc delta T, change in temperature, divided by temperature. Now we have an integral that we can do. That's going to be equal to the mass, the specific heat of water, and that integral is actually going to be a natural log, temperature 2 divided by temperature 1. So we can actually calculate out how much the entropy changes based on what the mass of the water was, specific heat of the water, and how much the temperature changed. So let's talk about entropy now in cyclic processes, such as the engines and refrigerators we were talking about earlier. It turns out that for any reversible cycle, then the change in entropy is going to be equal to 0. So we can write it kind of mathematically, delta S must be equal to 0. If we have some weird funky path like it's showing right here, essentially what the book says is, hey, we can approximate this weird funky path as a series of reversible Carnot cycles. So this weird funky path can be represented by these. Delta S must be equal to 0 for Carnot cycles, so a weird funky path can be represented by a bunch of Carnot cycles and have a change in entropy of equal to 0. It turns out that entropy is not like energy in that it is not a conserved quantity. If we have an irreversible process, the entropy of that system is always going to increase. So delta S for an irreversible process must be greater than or equal to 0. Actually, I think it's just going to be just greater than 0. So what that means is disorder is going to increase for non-reversible processes. Since the universe is made up of both reversible and non-reversible processes, in general, the disorder of the universe is trending upwards. So the universe is becoming less and less ordered. Kind of a scary way to think about things, huh? We can talk about entropy and how it's related to the second law of thermodynamics. It says, essentially, just like I wrote in the last slide, the total entropy of a system can never decrease. The total entropy of a system must be larger than or equal to 0. So that's kind of the mathematical way to talk about things, but let's just say what's going to happen if we have some water over here and we drop some red ink into it. Well, a little bit while later the ink's going to spread out, and if you just let it sit out in the room, the random motion of the particles is going to mix all of the ink pretty much uniformly throughout the water. So this is going to be much more disordered than this system right here, where we have the ink over here and the water over here. So here we have a much larger amount of disorder. We've never seen, and we never will see, spontaneous unmixing of the ink and the water. We can't just have something like this set up right here. It's going to look like this a little bit while later, and then it's going to essentially jump back into the bottle. Disorder will always increase.